Hey everyone, and welcome back to the Foundry by Forge College. So, in our previous explainer, Synthesis, Firedancer's role and next steps, we looked at how Firedancer fits into the broader Solana deployment picture. But today we're putting on our hard hats. We're going on a high-speed factory tour of Firedancer's internal plumbing. We're going to look at the exact validator architecture that makes this client just incredibly fast and efficient. Let's get right into it.
Now here's the massive question we really need to answer. How on earth does Firedancer process thousands of inputs without bottlenecking? I mean, think about it. If you've got this massive factory with thousands of parts literally flying in every single second, how do you avoid a complete, catastrophic factory jam? Well, Firedancer pulls this off through a brilliantly minimalist engineering design, and we're going to explore exactly how it manages this immense load without getting clogged up.
Okay, let's dive right into this blueprint. First, we'll go inside the Firedancer factory. Then, we'll meet the core components, check out handoffs and memory ownership, follow a transaction fast-track journey, and finally, look at balancing latency and throughput. Moving right along.
So starting off with part 1, inside the Firedancer factory, and specifically, how it goes about separating responsibilities.
At its very core, Firedancer takes the massive validator pipeline and breaks it down into distinct, hyper-focused components. But before we inspect all that machinery, we've got to ground ourselves with the raw materials coming in, right? Cloudbreak storage and proof of history, or POE. These are the core inputs Firedancer absolutely must ingest, verify, and apply at lightning speed. As you might remember from our earlier Advanced Solana Concepts modules, these are the fundamental data sources for any Solana validator. They're the essential raw materials our factory has to process flawlessly if we want to hit that top-tier performance.
All right, let's move on to part 2. Let's actually meet the core components, the factory workstations themselves.
Now, what's really interesting about what we're looking at here is how crystal clear the inputs and outputs are mapped out for every single Firedancer subsystem. Just look at the flow. You've got network ingress taking in UDP streams and outputting deserialized shreds. Then the SIG verify pipeline takes those exact transaction packets and outputs verified transactions. Same goes for the sequencer, banking, storage adapter, broadcast. Every single one has a dedicated spot, a clear input, and a definitive output. There are literally no blurred lines here, no confusion whatsoever.
Let's zoom in on that very first workstation, network ingress. Basically, this is the initial entry point. It accepts and decodes incoming shreds and transaction packets directly into pre-allocated memory buffers. Think of this as the factory's receiving dock. And honestly, the brilliant part here is that word pre-allocated. By having memory buffers just sitting there waiting, the system completely dodges costly memory allocation delays. It's exactly like having empty pallets lined up on the loading dock well before the delivery trucks even pull up.
Right after that, we hit the SIG verify pipeline. This is a dedicated stage that batches up transactions and performs CPU-bound cryptographic signature verification. So if the last stage was the loading dock, consider this the intense security checkpoint of our factory. We all know cryptographic math is notoriously heavy, right? By isolating this heavy lifting into its own dedicated stage, Firedancer ensures that all this complex crypto math doesn't bog down the rest of the assembly line. Which brings us to part 3, handoffs and memory ownership. Basically, the conveyor belts of our factory. So we have these isolated workstations, right? But they're kind of useless if the parts can't move between them efficiently. It all boils down to memory management. We can actually demystify this with a pretty simple office analogy. Think of owning memory like handing a coworker a physical clipboard. It completely eliminates copying, which makes it crazy fast, but it requires a clean, explicit transfer of ownership. Borrowing memory, on the other hand, is like making a photocopy of that clipboard. Sure, it's a bit safer and easier to manage, but it creates a ton of unnecessary CPU and memory overhead. Because of this, Firedancer heavily prefers zero-copy handoffs. They want to pass that physical clipboard every time to keep latency as low as humanly possible.
Let's move to the next step and see how this all builds together using a simplified Rust-style code pipeline. Step 1, we receive those UDP packets. Step 2, batch them up for group processing. Step 3, verify them by running that heavy CPU-bound crypto. And finally, Step 4, apply the state changes. It's a remarkably clean flow, isn't it? And hey, just as a quick aside, if you ever want to get into the weeds and understand the intricate coding patterns that make this kind of architectural separation a reality, the learning programs at Forge College are a totally fantastic way to master these concepts deeply.
All right, part 4. Let's follow a transaction fast-track journey and look at throughput in motion.
So those technical conveyor belts we just talked about, the ones linking ingress to SIG verify, those are known as inter-process communication,
or IPC paths. Firedancer relies on a few specific ones here. First, in-process lock-free queues, which give you incredibly low software overhead. Then you have cross-process shared memory rings, and this is exactly how the system pulls off those blazing fast zero-copy handoffs we mentioned. Finally, syscall-based pipes, which are used when high portability is needed. Choosing the exact right IPC channel here is absolutely crucial for keeping that latency down.
Okay, so once a batch is successfully verified, the sequencer steps in. The sequencer organizes these verified batches using proof-of-history sequence numbers, which then allows the bank application workers to proceed completely independently. Basically, you can think of the sequencer as the logical traffic controller. By tagging batches with POH sequence numbers, it ensures everything maintains serializability without, you guessed it, creating a massive traffic jam.
Now, when it comes to handling state, we hit the account storage adapter. This is an I/O interface that uses read-through caches and range prefetching to interact with Cloudbreak storage super quickly. And this brilliantly illustrates how, when the bank actually needs account data, it requests precise, surgical slices. It's not dragging around giant, heavy snapshots. This is exactly what keeps the actual state application moving lightning fast.
Moving into our final section, Part 5, Balancing Latency and Throughput. Time to tune the machine.
Running this kind of minimalist engineering marvel isn't just about flipping an on switch. We have to look at the operational trade-offs validators actually have to make when tuning this machinery under a heavy load. Notice this really tricky balancing act when it comes to batch sizes. Look at bar 1, small batches. You get great low latency, but pretty low overall throughput. Then there's bar 2, medium batches, which is a nice balanced approach. But check out bar 3, large batches. Collecting packets into large batches enables highly efficient vectorized crypto operations, which gives you massive throughput. But if it's left unmanaged, it can dangerously spike your tail latency. Basically, that means some transactions get stuck waiting way too long.
So how do you actually know if the machine is struggling? Well, you've got to watch these key telemetry bottleneck indicators. We're talking unchecked queue growth at handoff boundaries. We're looking at long-lived buffers. You might see mismatched stage processing rates, like say if ingress receives packets way faster than SIG-verify can even process them. And of course, high memory copy counts. If you're trying to diagnose Firedancer performance issues under a heavy load, these are the exact metrics you need to be looking at.
So I think the most crucial point here is captured beautifully in this quote. Separation of concerns, fast path processing should not block on slow path persistence. That right there summarizes the ultimate design philosophy of Firedancer's entire internal architecture. Let the fast, critical workers work fast, and handle all the slower tasks asynchronously, so the main assembly line never ever has to stop.
And that leaves us with a pretty provocative thought to wrap up on. Which of these components do you think will reveal the biggest bottlenecks when we explore scalability enhancements next? We've seen the pristine, perfect architecture today, but what actually happens when we push this system to its absolute limits? Well, we're going to tackle exactly that in our next explainer. Until then, I highly encourage you to head over to forge.college to learn more about this subject, dive even deeper into the architecture, and explore some other fascinating Web3 topics. Thanks so much for watching, and we'll see you next time.